let us go back to nature today, and remember we are doing optimization. So, does nature do optimization?
Yes.
Somebody said yes.
Ant colony optimization.
Yeah, but we are not going to study ant colony optimization. That is an algorithm that if we may not get time to look at it today, probably in the next class essentially. What is it? What is optimization happening there? Natural selection, which is different from ant colony optimization. Ant colonies are known to be very good at finding food. If you leave anything which is edible, a biscuit or a lump of sugar, then you can be sure that within some time ants would be there. Somehow they find it. We will look at that in the next class maybe. I think we will go to natural selection. So, you can think of course, many of us consider human beings to be the pinnacle of life forms. So, we can say we have come through a process of natural selection, which of course, is attributed, the theory is attributed to Charles Darwin actually, and you must have heard about the well known phrase survival of the fittest. But what is nature doing essentially? So, let us sort of step back and see what is it trying to do. So, we can say it is trying to design life forms essentially. So, we have a whole wide spectrum diversity of life on earth, starting with the cockroach, not starting with the cockroach, starting with some amoebas and ants and birds and animals, and so we think that we are at the top of it. What would be the objective of this design process, and what is it trying to design? I mean, if of course, we are trying to anthropomorphize thing by saying that nature is like trying to design something. Have you heard, how many of you have read anything by Richard Dawkins? Which one, which book have you read? The God Delusion. That is one of his more recent books, I think, in which he says that he is kind of anti institution of religion, but anyway, one of his earlier books was called the Blind Watchmaker. I don't know, it was quite a well known book, at quite a hit in that time. The argument in the Western society was whether or not there was a God who created the universe and the earth and human beings at the center of earth. And the argument was that everything is so perfect, the world is so perfect, we just have the right amount of oxygen in our air, and we have everything that we need, we have water flowing, and we have day and night and all this kind of stuff, that there must be a watchmaker. If the universe functions so perfectly like a Swiss watch, for example, I mean Switzerland is known for its mechanical watches, then it could not have come out of random. So, this was an argument against Darwin. Darwin said that we came out of evolution. So, people were aghast at the notion that we have evolved from apes. Sometimes I think the apes might be more aghast at this notion. But anyway, the idea was that such a perfectly functioning world must have a maker behind it, or the watchmaker, like a watchmaker. But Dawkins and Darwin's, they are all on the same side. They say that there is a built in ratchet mechanism in nature, in a sense that if you find some improvement somehow, then that improvement sticks around essentially. So, there is a ratchet mechanism. If you by mistake or by some chance event design something which works, then it has a tendency to persist. There is a person called Stephen Grand. He is somewhere in the UK. He wrote this book called Creation, which the institute has one copy, which is with me at this moment. So, if you want to have a look at it, you can come and borrow it, I think. You must have heard about creatures, right? These are computational fancies of people, life forms that you create in the so called cyber world, artificial fish, artificial this thing, artificial that. These are creatures. I mean, so the term creatures, so if you just look up creatures on the net, you will find some sites. One of them is maintained by Steve Grant. So, he is in this book that he wrote something very profound, at least I found it profound, and it is that whatever persists. Just imagine a random world where there is no watchmaker, there is no creator. He says that, see, this is a kind of a tautology, whatever persists persists, obviously. I mean, that is what we are saying, but this is the fundamental thing behind how life has emerged out of chaos, you might say, essentially. I mean, after Big Bang, I suppose there was chaos for a lot of time, and so if you follow what Steve Grant is saying, then you can say an equivalent statement that the goal of life. So, if life is some driving force or something, is to live, and by live essentially we mean persist essentially. That there is no, I mean, one cannot ascribe some external higher level goal to life. It just happens that we happen to persist, so we are there essentially. So, the goal of life is simply to be there essentially. Now, you can say that nature is experimenting. So, let me, I do not really need this. So, nature is, again, when we say nature, we do not want to anthropomorphize again. Nature is not like a god or some devta or somebody who is doing something. Nature is some term that we use for everything that is around us. Is sort of creating different designs for life forms. Okay. At least we can view it like that, that nature is doing it. See, very often people, for the sake of explanation, ascribe a design motive behind things which are happening. So, why did we develop a neocortex? Because it helped us reason at a symbolic level and things like that essentially. But of course, it is not, there is no motive behind that. It just so happens that we evolved a cortex which allowed us to do thinking. So, we are thinking essentially. So, which is what Steve Grant says, whatever persists persists essentially, and this is a basic mechanism behind nature's effort to design life forms, and the goal of this life form is nothing but to live, to persist essentially. I mean, that is our innate instinct to persist. So, if you were to walk out of this building and you see somebody with a gun pointing at you, the first thing you would do is run away or something like that essentially, right. So, that is our inbuilt nature to persist essentially. And if you think of it in combination with what Steve Grant is saying, just imagine that in the initial chaos there were only atoms floating around, then molecules formed, then molecules combined into forming bigger molecules, and then eventually organic molecules came into being, which had this tendency of surviving and sticking together, and then of course making copies of themselves and so on and so forth. Things which happen, and those things which survive, which is what Darwin called as survival of the fittest essentially. Of the many things that you are trying out, some things survive and they are the fittest essentially. So, when we say survival of the fittest, one has to look at it from a careful perspective, that it is not as if you are first determining fitness and then talking about survival. It is the other way around in fact essentially. When we say survival of the fittest, what we really mean is that the ones who survive are the fittest essentially. Now, these life forms compete with each other. What do they compete for? They compete for whatever resources that they need essentially, material resources, primarily material resources like food and so on, and there is a limited amount of food, and remember that food is a building, food provides us the matter for building our bodies essentially. So, if a child grows up, it is by eating food and having that food transformed into various things inside his system. So, they compete for resources which mean that some life forms succeeds and some life forms fail essentially. Just imagine that there is a bunch of people in a room, let us say there are 50 people in a room and there are only let us say 20 cakes or something like that, and of course, you cannot divide the cakes, let us assume. Then there is some mechanism by which people are given cakes. So, some 20 people will get cakes and 30 people will not get cakes, and to be taking an extreme point of view, those 30 people will die and only those 20 will survive or something like that. This is a very extreme view, but in some sense this is what is happening in nature essentially, that different life forms are like different species and nature is experimenting. Again, I would like to sort of caution that when I say nature is experimenting, nature is not like a person sitting out there who is experimenting, that these things are happening on their own and we can view them as experiments essentially. So, how is nature doing? Nature is doing generate and test. It is searching. Remember that we started off by saying that the basic paradigm of search algorithm that we are going to look at is generate and test. Generate a candidate and test whether the candidate is a solution. That we had a smaller problem. Nature does not have a goal, so it does not have a goal test function, but by testing we mean something else here. So, what do we mean by generate? So, there was a French poet, I do not remember his name unfortunately right now, who put it very succinctly. He said this process that the world, this process of evolution is that one makes up the combinations and the other chooses. So, there are two forces which are applying. One is which is making up the combinations, which we will call as generate, and test is basically the other chooses. So, these are two things essentially. What do we mean by the other chooses? In the sense that there is a force which natural selection, which says that it will select some people who will survive and well not people, some creatures which will survive and some which will not survive. So, there is a selection happening which is like a test function, and there is a process of generating, creating new creatures is happening. And so, just imagine this world in which new creatures, and by creatures I mean individuals, are being created all this time, and each of them is competing with other creatures. They may be from the same species or they may be from a different species, but everybody is competing for food essentially. So, at the fundamental level, I mean that is our strongest basic urge, is to eat essentially, and that without that we cannot survive essentially. How does this combinations come about? Okay, let us talk about the other choices before we do that essentially. So, just imagine that there is a rabbit or there is a species of rabbit, and there are these rabbits on this field, and they are being chased by foxes also, let us say on the same field. So, there is a relation between them, the fox species and the rabbit species, and I will use this as a edge which denotes a positive influence on the population essentially. So, this is like some people call influence diagrams. How does the population of rabbits influence the population of foxes? We say that it is a positive influence, in the sense the more the rabbits are there out there, the more the foxes will get to eat them, and therefore, the foxes will survive essentially. So, the more, so there is no famine of rabbits or something, and of course, there is a negative influence of the population of foxes on rabbits essentially, and so on. Then of course, there is this whole ecosystem out there. So, when you have foxes, then you have let us say tigers, and when you have tigers, you have let us say bacteria, and you must be familiar with this essentially. The birds help pollinate the flowers, and there is a dependence, there is a whole ecosystem there, which is a stable ecosystem, in which every population is having some influence on other populations essentially. So, nowadays one hears that if suddenly if bees vanish from this world, you might have heard some news item that if bees vanish, then it will affect a certain food chain, which will will stop getting things of a certain kind. So, we have this stable ecosystems, but we also have catastrophes on the way essentially. So, like 60,000 years ago or whatever, when the predominant life form was dinosaurs and so on, and mammals were small scurrying creatures hiding from dinosaurs, but suddenly something happened and we do not quite know what happened, and dinosaurs became extinct and mammals became prominent, and then humans of course the most prominent of us all essentially. So, we are talking about competition, right. There is competition between species. So, let us say we have rabbits and cows and goats and sheep all trying to go for some food. I do not know whether rabbits eat grass, but at least cows and goats and sheep all competing for grass essentially. So, there is competition between species, but there is also competition within the species. So, we are going to focus on this competition within the species. What do we mean by this? So, just imagine again this bunch of rabbits on this field, and let us say 2 or 3 foxes come running and the rabbits all run away, or more likely if you have watched some wildlife films, it is a sort of bunch of deer and 1 or 2 lions come running, then all the deers are running away and the lion catches the in some sense the weakest one essentially, the one which cannot run away fastest. So, the lion catches the weakest one and the fastest deer they escape essentially, they go and live to tell, as they say, another tale. So, there is competition within the species. So, if there is a prey and there is a species on which is preyed upon, there is competition within the species to escape or to catch food essentially. So, again the strongest lions will be able to catch deer, by strongest we mean fastest. So, whatever is a good quality, the fastest rabbits will be able to escape. So, fastest is just a attribute I am using, it is not necessarily fastest, it could be something else, cleverest, or something which can disguise itself very well, or any kind of things that nature adopts to. So, there is a constant battle between the predator and the prey essentially, right. Both are evolving. How are they evolving? Because within the competition within the species is selecting better and better individuals which are propagating their properties in some fashion to the next level essentially. So, that brings us to one makes up the combinations. So, what is the combination that nature has adopted? It is of sexual reproduction and what does it lead to? It leads to genetic mixing. This is the key. How does nature experiment with different life forms? It mixes up genes of individuals. So, every creature is, at least on this earth, is born of two parents and inherits the genes from both the parents, and then of course, there is this whole theory of which are the dominant ones and which are the recessive ones and that kind of stuff, but eventually there is a experimentation with newer and newer combinations of genes that life is doing. So, we use the term genotype for this. Nature is experimenting with the genotype of, so genotype is like the design of a creature. Right. So, of course, amongst human beings we say that this child has inherited the height from one parent or both parents or something like that essentially, or color of hair or color of eyes, all kinds of things you inherit from a parent. So, you inherit some from one parent, some from another parent, and within a human family one sibling may be brighter than another sibling, and things like that, because they have inherited different things from different parents and so on. So, we have this whole churning of the genes which is happening in with the genotype, and at this other level which we call as a phenotype. This competition is happening. It is a physical creature which is competing out there in the real world essentially. So, what does this have to do with optimization? We want to look at a method of optimization which is kind of takes inspiration from this world of natural selection. So, this whole idea here is that of emergent behavior. And the idea of emergent behavior is that you put together simple parts to give you a more complex thing essentially. So, nature is it has these building blocks of life which are called the genes that we have, and nature is trying out different combinations of genes and letting them loose in the world, and if they survive, they survive. So, they are competing for food, they are competing for mates, they are competing for shelter. The ones who manage to win, they will pass on their genes to the next generation, and in the process we will have in some sense fitter populations of. So, the population of rabbits becomes faster, again I am using faster just as a way of talking about it. As they evolve, they become faster, at the same time foxes are becoming faster. So, there is a sort of war going on between them essentially. So, emergent behavior is this approach to optimization which says let us try to do this so called random mixing of genes. So, again this is a randomized process and see if we can somehow keep track of the best ones. So, what is the basic idea? You allow for random mixing of genes and you have a mechanism for keeping the best. So, this thing one makes up the combinations and the other chooses. So, there is two processes, one is combining things, this generate and test, one is combining things to produce new creatures and there is some mechanism which is judging. So, which creatures are good, which creatures are bad and allowing them to survive essentially, and in the process we want to see if we can improve upon the designs and come up with the optimal design, whatever optimal means here. So, this idea of optimization is called by the name of genetic algorithms. Also called GAs for example, and they were devised around 1980 or so by one John Holland and one of his students called David Goldberg is still very active in this area, and in fact he has written a book which is called Genetic Algorithms or something like that, which is a very popular book on this topic essentially. So, the idea of genetic algorithm is that they work with populations. So, the first thing of course is you have to, first step is to encode we are working in the solution space. So, you have to encode a solution as a string. So, I will just use the term string, but if I were to be from this community, instead of string I would say chromosome. So, it is the chromosome which sort of contains the design decisions that you are going to work with, but we will tend to think of it as a string essentially. So, the first thing is to encode the solution as a string. So, the simplest example that we can think of is the SAT problem, where the solution is just a bit string essentially, or TSP can be encoded as some sort of a string, and for any kind of a problem that you want to solve with GAs, you have to encode it as a string essentially. So, this population is a population of strings essentially. So, this population P1 to Pn, let us say we have n population of n elements inside this is. Then the next thing you want to do, so first thing is to encode candidate solutions as string essentially. So, essentially what are we trying to do, that we will work with a population of initial randomly generated candidates and then try to mix up the strings to produce new candidates, which will hopefully be better essentially. And how do we decide better? So, we do not let loose these things into the designs into the real world as nature does. We devise something called a fitness function. Let us say f of n, which is the same as what we call eval of n, which was the same as what we call of h of n to start with. Remember that we came to this world of optimization by starting with the heuristic function, and then we said the evaluation we called it the evaluation function because that is what the optimization community calls it, and in particular the genetic algorithm community calls it a fitness function essentially. So, with every candidate we have a fitness value which tells us how good that candidate is essentially. I have to see how much time we will have. Okay. So, there are three basic steps to a genetic algorithm. So, we start with an initial population P, and then the first step is the. So, this is the preliminary work that we are doing, designing the system, but the algorithm itself, the GA algorithm has three steps. The first step is called selection, which is proportional to fitness. So, unlike the real world, genetic algorithm does cloning essentially. So, it just creates copies of candidates. So, what do? We have these candidates P1, P2, P3, Pn, and for that each of them we have a fitness function, and we reproduce this population, clone this population, we clone individuals in this population in proportion to their fitness, which means we will make more copies of fit candidates and less copies of unfit candidates, less meaning 0 basically, or more could be 1, 2, 3, 4 anything. How do we do this? We create, it is a similar process to, how do we create this whole random process? We can think of it as a roulette wheel in which we assign sectors proportional to their fitness. So, this is P1, this is P2, this is P3, P4 and so on. The amount of angle they get is proportional to their fitness value. So, P4 is very fit, so it gets a large angle, P3 is and so on and so forth, and we just sort of rotate it randomly and we have some pointer. So, wherever it stops, that candidate gets to reproduce once. So, we rotate it, let us say it stops with P4. So, remember that this is something which can rotate, and we give it a random rotation like a roulette wheel and observe where the needle is. We do this n times and generate n new, a population of n new elements. So, let us call it P1 prime, P2 prime, Pn prime. So, this is the first step, selection. We are just making copies of the original, but with the difference that everyone does not get to make a copy. Fit members have a greater chance of making more copies, as you can see it is very likely that P4 will stop at the P4 will stop at this arrow more than once essentially. So, P4 may get more copies, this thing whatever it is here will probably get 0 copies or something like that here. But of course, it depends upon chance, the randomized algorithm we cannot say deterministically what will come about it. All we are saying is that this roulette wheel we will spin n times and whichever names of the candidates appear against the needle we will create a copy of that, and so we will create a new population of n candidates, and you can see that this population the fit members will have a greater chance of appearing more than once and unfit members may get weeded out essentially. So, there is a little bit difference of what happens in nature. We do not create the final thing, final individuals and send them out to compete. We allow them to clone in proportion to how good they are essentially, and they can get to clone more than once. After that is the second step is called, in terms of the GA community, it is called crossover. And what do we do here? We randomly pair this population. So, for example, we may pair P1 with some other one, P2 with somebody else and so on and so forth. We randomly pair of this elements of this new population and we randomly mix up their genes. That mix up of genes is called crossover, and that is just a term that we use. So, the idea is something like this. For example, let us say P1 is made up of, let us say, genes which we will call X, let us say that there are 9 components to this. For example, if it is a SAT problem with 9 variables, then there would be 9 bits. So, we are just calling them x1 to x9. Then P2, so let us say P1 has been paired with P2, or you can call it Pi and Pj, it does not matter. So, since I am using, okay, let us say Pi and Pj, and let us call this y1, y2, y3 up to y9. So, we have these 2 parents. So, P1 and Pi and Pj are the 2 parents which have been mated together by this random process of mating. We just randomly mate 2 elements and then we want to mix up their genes. So, one way of doing it is to just draw a line somewhere and generate new children. So, C1 is equal to, we take x1, x2, x3, x4 from here and then y1, y5, y6, y9 from this. The other child gets the other genes. So, this will get y1 to y4 and x5 to x9. This process of mixing up genes is called crossover, and you can see why it is called crossover is that some genes are crossing over from one candidate to the other and vice versa for this. This particular crossover is called a single point crossover. But you can devise other crossovers. I mean, there is nothing sacrosanct about this single point crossover. Just to illustrate, we have done this, that we will randomly choose a point here and everything on one side will go to one child and the other side will go to the other child, and likewise for the other this thing. So, you can imagine a SAT problem in which you get first 4 bit values from one candidate, one solution, and the next 5 bits from the other parent essentially, and likewise for the other child essentially. So, you can see these two components that we talked about. One makes up the combination is being done by the crossover part, and the other chooses is being done by the selection part essentially. and we basically put this into a loop essentially. We take a population, generate a new cloned population, do crossover and go all over again. Now, for the sake of completeness, that sometimes a population may be lacking a gene essentially. So, or how do new kinds of species emerge out of this process essentially. We have a third step. So, the first step is selection, the second step is crossover, and the third step is called mutation, and by mutation we mean random, and not only random, it is a rare event. Every once in a while you change one gene randomly in one individual. So, we have this whole population of n elements here, which is reproduced according to fitness, then we do crossover to mix up the genes, and then we make some random change in one candidate. Okay. So, this is just to allow for new genes to come in, or if a, so for example, if you have a population of this SAT problem, let us say this 9 variable SAT problem, and you have a population of 50 candidates, and it so happens that all 50 of them have their third bit as 0 essentially. Now, you can see that if all 50 of them has their third bit as 0, then however much you do this churning, the third bit will remain 0, because both parents are going to have the third bit as 0, and this crossover operation will result in the third bit being 0 in both the children essentially. So, you have lost that third bit in some sense. To cater to something like that, we have a random change somewhere, mutation, but we do it very rarely essentially. This is just for the sake of completeness. So, the primary process is selection and crossover, but there is a process which once in a while we do, which we make some change in some candidate essentially, some random change in some candidate. So, when we talk about SAT, we are talking about bits, but otherwise we have to do this encoding into the chromosome in a more careful fashion, and then we have to, because one bit is nice, but for most problems you cannot have a component represented by one bit, you will have a chunk of bits, then you have to devise your algorithm to move around chunks of bits rather than just single bits, and then you have to be careful about mutation, that you can change, you mutate something into something meaningful and not something which is not meaningful, and so on and so forth. So, from this we get a new population, let us call this P 1 prime prime, P 2 prime prime up to P n prime prime. So, the first P prime population we got by cloning, and this P prime prime population we got by crossover essentially, and let us say mutation has been taken into account here essentially. Now, there are variations to what people do at this stage. If you assume that these are sorted on fitness values, that these are the best on the, just for the sake of processing, these are sorted, the most fit members are here and the least fit members are here. So, what one might do is that one might take the most fit k elements, where k is a little bit smaller than n, and replace it in the original population by the with the least fit k elements. So, what are we doing here is that we started with this population of n elements, and let us assume that they are sorted according to fitness here, just for the sake of allowing me to draw this diagram. We clone the entire population to get a new population, and when I say entire population, it means that you get representation in proportion to your fitness value. A very fit member will get more copies, a very unfit member will get less copies or 0 copies, some will have to have 0 copies. Then you do this crossover, mix up the genes to arrive at this population, which has now mixed up the genes of the old ones. Now, some people would argue that what if there was a very good candidate here, this P1, let us say its fitness value was 98 or something like that, and everything else let us say began with 67 and 65 and so on and so forth. Are not you losing that candidate with fitness value 98 essentially? To cater to this, one way to devise this is that you take the most fit k most fit candidate in this new population and add them or substitute this least k fit population with this most k fit population here, keep those few top from the original population here. This is just a design question. You can say k equal to n, and that is what really happens in nature actually. I mean nature does not allow one to live indefinitely essentially. Okay. Now, if you were to read some of this work by Goldberg, in fact this book by Goldberg, then he goes on to study as to how should we design this encoding scheme so that good genes in some sense have a tendency to stick together and carry forward essentially. So, let us say if we have this some or let us say this SAT example with 9 genes or 9 variables, and let us say some good values we have found in some candidate where let us say x3 and x4 we have found what should be the value in the ultimate solution. How do we kind of make sure that they stick around together essentially? So, Goldberg talks about things like clusters of genes and so on, which will, so he calls he has some notion of saying that if you have genes which sort of are designed kept together, then they will stay together, they are more likely to be not split, broken up essentially. So, essentially one of the things with this genetic programming or genetic algorithm community is concerned with is that is there some way we can ensure that when a candidate has good genes, we can ensure that the good genes stay together essentially and they do not get broken up and divided in, because in this case as you can see it is a very clear cut exchange of genes essentially. Every gene of a parent, for example, if x3 is a good gene, it will go to exactly one child in this way, in this scheme of things, because C1 will get x3, but C2 will get y3 essentially. So, it is not as if as it happens in the real world that a good gene can go to both the children. In this case it will go to only one child. So, if x3 and x5 for example happen to be good genes, how can we sort of ensure or can we ensure that good genes stay together, which means they stay in one candidate only essentially. So, this is the kind of stuff which Goldberg has looked at. We will not go into those details here, but you can see that this scheme of things where we select the k best and replace the k worst with this k best is in some sense trying to keep the good candidates still alive essentially. Of course, this P1 prime prime, which is a totally new candidate because it is got generated by this crossover, it could be P1 crossover with some other element, is totally different and it could in fact be better than 98, it is quite possible essentially. That is a hope that as we mix up genes, the candidates with the good genes will propagate their genes more often, and we are ensuring this by the process of selection which is proportional to fitness essentially. So, I think I will stop close to here. If there are any questions we can answer them. In the next class when we meet, I will take up an example again from Goldberg's book to try and give you a good intuition behind genetic algorithms. But I also want you to think about our not our, the community's favorite problem, which is the traveling salesman problem. How can we use genetic algorithms for solving the traveling salesman problem? So, at the very outset, let me say that because the way that we have encoded TSP so far is that let us say we have 9 cities. So, let us say parent 1 is 1 2 3 7 1, and parent 2 is let us say 1 2 3 4 5 6 7 8 9. I have these 2 parents, which means I have these 2 tours. So, here you go from 2 to 3, 3 to 7 and 7 to 1 and 7 and so on. Here you go from 1 to 2 and 2 to 3 and so on and so forth. You can see that this single point crossover will not work here, because if I just take a random point, let us say here after 4 cities, then what am I doing? I am going from 2 to 3 to 7 to 1 to 5 to 6 to 7. So, as you can see, I have closed the loop even before. I am not allowed to do that. In a traveling salesman problem, the solution must be a permutation of the cities. But if I do this single point crossover and say this is, I will take this cities from here and this cities from here, what I get is not really a candidate tour, because this tour has a loop inside before. So, you are going from 2 to 3, 3 to 7, 7 to 1, then you are going to 5 to and then to 6, and then you are coming back to 7, and you are never visiting some cities. You are never visiting 4, you are never visiting 8, you are never visiting 9. So, that is not a candidate solution. What we want is a population of candidate solutions, and what is a candidate solution? In which every city is visited exactly once, and then which means basically it is a permutation of the numbers 1 to 9, and this sequence of numbers is not a permutation, because 7 is repeated and 4 is missing essentially. So, it is not a permutation. How can we devise crossover operators for the TSP essentially? So, this question is in 2 parts. Can we think of a different representation of that candidate solution, and can we think of different operators, different crossover operators? And there has been a considerable amount of work done in trying to experiment with different kinds of crossover operators. So, we will generalize the notion of crossover to say that you take 2 parents and you must somehow get 2 children which are generated from those 2 parents. So, these 2 things we will do in the next class. To start with, we will look at an example of genetic algorithms for a simple problem, and then we will look at how TSP can be solved using GAs, and I want you to give some thought to it before you come to the next class. Okay, so we will stop here, I think.